Hello everyone, welcome to the lecture series of Engineering Mathematics 1. This is our fourth lecture on partial differentiation. Here we are going to see Euler's theorem on homogeneous function with proof. Okay, so first of all in this lecture we are going to see the proofs. These proofs that are going to ask in examination. Okay, so one of the proof may be there in exam. So let's see the proof for this. First of all, what is a homogeneous function that we are going to see here? Okay, a homogeneous function is one with multiplicative scaling behavior if all its arguments are multiplied by factor, then its value is multiplied by some power of this factor. Okay. For example, a homogeneous real valued function of two variables x and y is a real valued function that satisfies the condition f of k into x, comma k into y is equal to k raised to n f of xy for some constant k and all real numbers alpha. Constant k is called the degree of homogeneity. Means if suppose I am having a function, say I am having a function here f of xy is equal to x cube plus y cube upon x minus y. Okay, suppose this is a function given to us. Now here you can check. If I replace here x by xt and y by yt, what we have to do? We have to put here in this function x equal to xt and y is equal to yt. Then what happens here? xt whole cube plus yt whole cube upon xt minus yt. Okay. Now here, if you open this cube, it will go to the each term x cube t cube plus y cube t cube upon xt minus yt. Okay. Now in numerator you can check t cube is common. Then what is remaining? X cube plus y cube. Okay. Divided by, now at denominator you can check here t is common. Then x minus y is remaining. Okay. Now see here, t cube divided by t means it is t square. So what is remaining? X cube plus y cube upon x minus y. Right? So you can check here, when you replaced your x by xt and y by yt, you get the function where you find t square common, and this is your original function. You can check here. Okay. So accordingly this must satisfy this definition. Okay. Now to check whether this given function is homogeneous or not, we can use this alternative method also. If we can represent a function in this format, then also we can say it is a homogeneous function. Okay. See how we can show that. So here, now what I am going to do, if suppose I am having a same function f of xy is equal to x cube plus y cube upon x minus y, and I find here x cube common in numerator. Okay, then what is remaining? 1 plus, now here there is no x cube, so I have to divide here by x cube, right? So divide the term by x cube. Then at denominator what you have to do? Find x common. Okay. And you can write 1 minus y upon x. Okay. Now see here, I can write this is x square in bracket 1 plus y upon x whole cube upon 1 minus y upon x. And you can check this is a function in terms of y upon x. Okay. So this satisfies this condition. And what is the degree here? N. And what is value for n here? 2. Okay. So I hope you all understand what is homogeneous function. You have to check in numerator and denominator. Okay. In numerator, each term should have degree same. And in denominator, each term should have degree same. Okay. Doesn't matter in numerator and in denominator whatever is the degree. ये जरूरी नहीं है कि न्यूमरेटर और डिनोमिनेटर की डिग्री सेम होनी चाहिए. Okay. So let's have here Euler theorem. Let's see what is the statement for this Euler theorem. So this is a statement: if u is a homogeneous function of x and y of degree n, then x into dou u by dou x plus y into dou u by dou y is equal to n into u. Okay. Now see, what is a given part here? If u is a homogeneous function of x and y, means it is given that u is homogeneous function of x and y. That is a given part. Okay. And degree of this homogeneous function is what? N. Okay. And we have to show that this one. And to prove x into dou u by dou x plus y into dou u by dou y is equal to n into u. This we have to show here, right? So see, from the given part, u is homogeneous function of x and y of degree n. From this we can know that from given, if your function is homogeneous, let u is equal to x raised to n f of y upon x be the homogeneous function. Okay. Of degree n. We can consider. Now differentiate this u with respect to x. What we are going to do here? We are going to solve this left hand side. And to solve this left hand side, I have to find this dou u by dou x and dou u by dou y. These two partial derivatives here. Okay. So I have to differentiate this u with respect to x and with respect to y partially. Because u is a function of two variables x and y. So what we are going to do? Differentiate u with respect to x partially. Okay. Now here we are differentiating with respect to x partially, means what? Here y is constant. But you can see this is a function of x and this one is also a function of x. There are two functions of x, right? So we have to use a product rule while differentiating. Okay. So here dou u by dou x is equal to, if suppose this x raised to n is constant first time. Okay. Keep it constant and derivative of this function f. What is the derivative? I can write here f dash of y upon x into derivative of y upon x with respect to x. So y is constant and derivative of 1 upon x, it is minus 1 upon x square. Okay, I hope you understand. Then plus. Now suppose this time f of y upon x is constant. Okay, here this function is constant now and taking a derivative of x raised to n. So what is the derivative of x raised to n? Using a standard result. What is it? N into x raised to n minus 1. Okay. So here what I can write now, see on left hand side your partial derivative dou u by dou x, it is multiplied by x. So from this I can multiply this partial derivative. So multiply by x. Why I am multiplying by x? Because it is in our left hand side. Our partial derivative u with respect to x is multiplied by x here. Okay. So that's why I am going to multiply this partial derivative by x. Okay. So what I will get here then? X into dou u by dou x is equal to, so see here, x raised to n into y into minus 1 upon x square. So when I multiply here by x, what happens? One x here get cancelled, right? So here can I write it x raised to n upon x into y? Okay, and this will be negative because of this negative sign, right? And what is remaining? F dash of y upon x, right? Plus, similarly, I am going to multiply by x here. Okay. So, you can see when I multiply this term by x, I will get this term. Okay. So, this is a multiplication by x. Now, let's simplify the term. So, here, what I have to do, x into dou u by dou x. Okay. So, I can write here x into dou u by dou x is equal to, okay, let's simplify the term here. This x is dividing here to this x raised to n. So, if I transfer this in numerator, it will be x raised to minus 1, right? So, I can write this minus x raised to n minus 1. Base is same, so we can add the powers of that term, right? Next is this remaining terms I have to write y into f dash of y upon x. So write down here y into f dash of y upon x plus, now the next one, see here x into x raised to n minus 1 is there, right? But already here x is in multiplication. So its power is what? 1. Base is same. Again adding the powers of this term. So this plus 1 and minus 1 will get cancelled. So what is remaining? N into x raised to n into f of y upon x. Right? So I can write here n into x raised to n into f of y upon x. Okay. Now I got here this term x into dou u by dou x. So I hope till now you all understood the example. Okay. Now next is what? I want to find this y into dou u by dou y. So this time I am going to differentiate this u with respect to y. Okay. Why I am going to differentiate this with respect to y? Because I have to find here dou u by dou y. Okay. So differentiate here. Differentiate u with respect to y, keeping x constant. Okay, I hope you all understand. So you can check here what is your function. U is equal to x raised to n f of y upon x, and I am differentiating these now with respect to y. So x is constant. See, there is only a single term for y. And this x raised to n is constant. So now this time I don't have to use product rule. I am directly going to differentiate this f of y upon x with respect to y. Okay. So x raised to n dou u upon dou y, derivative of u with respect to y. X raised to n is constant here. And derivative of f of y upon x. What is it? F dash of y upon x into derivative of y upon x with respect to y. So 1 upon x is constant and derivative of y is 1. Okay. Now here, let's simplify the term. See, x raised to n upon x means I can write this term x raised to n minus 1. Okay. Into f dash of y upon x. Right. But dou u by dou y here, if we check the left hand side, it is multiplied by y. So I am going to multiply this term by y here as per the requirement. Okay. So let's multiply by y. Okay. So I hope you all understood why we are multiplying here this term by y. Okay. So y into dou u by dou y is equal to, this is our term, multiply this term by y. So it is y into x raised to n minus 1 f dash of y upon x. Right. Now see here, let's say this is equation A and this is equation B. Okay. Now what we have to prove? This one. So I can consider here left hand side. What is the left hand side? Say this is equation 1. Let left hand side is equal to x into dou u by dou x plus y into dou u by dou y. Okay. We have to solve this. Now we have the value for x into dou u by dou x. What is the value for x into dou u by dou x? This one. Take here. Okay. And what is the value for y into dou u by dou y? This one. So you can check here, if I add these two equations together, this term and this term, if you check, both are same, but their signs are opposite. This term is negative and this term is positive. So when I add this one, okay, that will cancel each other. So what is the remaining term here after doing addition on right hand side? Only this term. Right. So n into x raised to n f of y upon x. Right. So here n into u. Why u? Because what is the value for u here? You can check x raised to n into f of y upon x. So I can replace this x raised to n into f of y upon x by u. Hence proof. So I can write here x into dou u by dou x plus y into dou u by dou y is equal to n into u. Hence proved. Okay. So these proofs are very simple. Don't get scared. Just you have to use the homogeneous function definition. Okay. So first of all, you have to take this homogeneous function. Right. Now this is a main statement of Euler's theorem. And using this Euler's theorem statement, we have three deductions. Okay. So let's have a proof for that 3 deductions here. That are also important because in examination you have to solve examples based on it. Okay. So see here, this is the first deduction of Euler's theorem. Okay. Last time what we have seen, it is a first order differential equation. Now this time it is a second order differential equation. And this we have to solve here. Okay. So here, first of all, you have to write given part. What is the given part? U is homogeneous function of x and y. Okay. Of degree n. And we have seen when u is a homogeneous function of degree n, then by Euler's theorem. Now we can use that Euler's theorem here. So by Euler's theorem, okay, what we can write? A first order differential equation that we have shown right now, x into dou u by dou x plus y into dou u by dou y is equal to n into u. This we have shown, right? So whenever there is a function which is homogeneous of degree n, we can use this equation. Okay? So x into dou u by dou x plus y into dou u by dou y is equal to n into u. Let's have this is our first equation. Now see what we have to show, this one. And here there are partial derivatives of u that are second order derivatives. Means I have to differentiate this equation again. First with respect to x and then with respect to y. Just I have to do this. Okay. So let's differentiate here. Differentiate equation 1 with respect to x keeping y constant. Okay. So see here, I am differentiating this equation with respect to x again, right? So I have to use here product rule because this is a term depending on x and this is also a term depending on x, right? So if suppose I keep here x constant and I take a derivative of this dou u by dou x with respect to x, this will give me second order derivative dou 2u upon dou x square. If I again differentiate, okay? Then plus, now suppose this time dou u by dou x is constant. So dou u by dou x and derivative of x, it is what? 1. Plus y is constant with respect to x. So keep it as it is and we have to take a derivative of this term only. So that will give you dou 2u upon dou x dou y. Already there is a derivative of u with respect to y. Okay. But when I differentiate this again with respect to x, that will give me a mixed derivative. Mixed double derivative of u with respect to x, y. Okay. Then equal to n. N is a constant with respect to x, right? And taking a derivative of u now. So that will be derivative of u with respect to x. Okay. Now here I got this term, but you can see on left hand side this double derivative of u with respect to x is multiplied by x square. Already there is 1x. So again I have to multiply the term by x here, right? So multiply here, multiply by x to this equation. What I will get? X square dou 2u upon dou x square plus x dou u by dou x plus xy dou 2u upon dou x dou y is equal to n into x dou u by dou x. Okay. Now next, say this is our equation A. Similarly, I have to differentiate now this equation 1 with respect to y to have this double derivative of u with respect to y. So now this time differentiate equation 1 with respect to y keeping x constant. Okay. So see here. Now I am differentiating this time with respect to y. So x is constant. So I have to take a derivative of this term only here now. So what will be the derivative? See, x is constant and with respect to y, dou 2u upon dou x dou y, because there is already a first derivative of u with respect to x, right? Now plus. Here you can see there are two terms that are depending on y. So I have to use a product rule. So suppose first of all y is constant. Taking a derivative of these terms with respect to y, that will give you dou to u upon dou y square plus. Now suppose this dou u by dou y is constant now and derivative of y is 1. Right? This time this term is constant and derivative of y, that is 1. Okay. Equal to, now see, n is constant. Right? And taking a derivative of u with respect to y. So that will give you dou u upon dou y. Right? But if you check your second order derivative of u with respect to y, it is multiplied by y square. And here second order derivative is multiplied by only y. So I have to multiply this equation by y again. Okay. So multiply y by y to equation. Which equation? This equation. Okay, that we have find right now. अब इस equation को अगर y से multiply करेंगे, what we get? Yes, it is x into y dou to u upon dou x dou y plus y square dou to u upon dou y square plus, see here, multiply by y, so that will be y into dou u by dou y equal to, here also multiply by y, so that will give you n into dou u by dou y, multiply by y. Okay, so say this is your equation B. Now we have to prove this one, right? So now what we are going to do? We are simply going to add equation A with equation B. Okay, so see here, this is our equation A and this is the left hand side of the equation A. Okay, so first of all I am going to write the left hand side here. So it is what? From equation A, it is x square dou to u upon dou x square plus xy dou to u upon dou x dou y plus x dou u by dou x is equal to, plus. Okay, because we are going to do addition. Now write down a left hand side of this equation B. So that is xy dou to u upon dou x dou y plus y square dou to u upon dou y square plus y dou u by dou y is equal to, now the right hand side of equation A, n into x dou u by dou x, right? N into x dou u by dou x plus right hand side of the equation B, n into y dou u by dou y. Okay, now just simplify this one. So x square dou to u upon dou x square plus xy dou to u upon dou x dou y plus xy dou to u upon dou x dou y. There are two terms, so I can write here 2xy dou to u upon dou x dou y plus, okay, this term I am going to write y square dou to u upon dou y square plus, now this term we can write here x into dou u by dou x plus y into dou u by dou y, that is equal to, now see, from the right hand side of this equation, what I can find here common? Yes, n is common. So if I take here n is common, what is remaining? X into dou u by dou x plus y into dou u by dou y. Okay, but I have the value for this one, x into dou u by dou x and plus y into dou u by dou y. What is that value? See, from equation 1, I can write the value for that. It is n into u, right? So putting this value from equation 1, can I write it x square dou 2u upon dou x square plus 2xy dou 2u upon dou x dou y plus y square dou 2u upon dou y square plus, replace this one by nu, then n into nu. Okay. Now transfer this term on the right hand side. So this will give me x square dou 2u upon dou x square plus 2xy dou 2u upon dou x dou y plus y square dou 2u upon dou y square is equal to n into nu minus, transfer this term on right hand side, that will be again nu. So if I find here n into u common, okay, see here, this n into u, if I find common, what is remaining? N minus 1. And you can check, this is our required term, n into n minus 1 into u. So you have to remember, when your function is homogeneous of degree n, okay, then by Euler's theorem, I can write for first order differential equation x into dou u by dou x plus y into dou u by dou y is equal to n into u. And for second order differential equation, I can write x square dou 2u upon dou x square plus 2xy dou 2u upon dou x dou y plus y square dou 2u upon dou y square is equal to n into n minus 1 into u. This you have to remember. Okay. So when u is homogeneous, then you can have two possibilities, or you can have two equations, first order relation and second order relation. Okay. Now this is the first deduction that we have taken from Euler's theorem. Now the next deduction also we are going to have from this Euler's theorem. Okay. Okay. So here next deduction is from Euler's theorem is that if z is a homogeneous function of xy of degree n and z is equal to f of u, then x into dou u by dou x plus y into dou u by dou y is equal to n into f of u upon f dash of u. This we have to show. Okay. Now see again from given part. First of all, always you have to remember, you have to write down a given part. So what is a given here? See, z is homogeneous. Okay. Z is homogeneous function of x and y of degree n. Now this time concentrate, z is homogeneous, not u. Okay, z is homogeneous of xy of degree n. So by Euler's theorem, what I can write? Yes, x into dou z by dou x, not u, because z is homogeneous. Okay, so x into dou z by dou x plus y into dou z by dou y is equal to nz. Okay, but what is the value for z here given to you? F of u, right? But z is equal to what? F of u. So replace here in equation 1. So what I can write? From equation 1, then I can write x into dou by dou x of f of u plus y into dou by dou y of f of u, that is equal to n into f of u. Just I have replaced here value for z, that is f of u. Now see here, dou by dou x of f of u means I have to differentiate this f with respect to x. So what I can write? X into f dash of u, and then again a derivative of this u with respect to x. So that will be dou u by dou x plus y into, again derivative of this function with respect to y. So that will be f dash of u into derivative of u with respect to y, that is dou u by dou y, that is equal to n into f of u. Okay. Now see here, I can take this f dash of u common. So what is remaining? If I take f dash of u common, yes, x into dou u by dou x plus y into dou u by dou y is equal to n into f of u, right? Now see here, I can divide by this f dash of here. So what I will get? Yes, x into dou u by dou x plus y into dou u by dou y is equal to n into f of u upon f dash of u. Okay, hence proved. See, it is a very simple proof. Just you have to concentrate which function is given as homogeneous, and accordingly we have to solve the example. We have to use here a given part very accurately. Okay, so z is homogeneous, so I can use the Euler's theorem for z, right? And value for z is what? F of u. Okay, so if this kind of function is there, its first order relation value by Euler's theorem is n into f of u upon f dash of u, not n into u. Okay, I will explain you the difference between two by taking an example that will more make you understand. Okay, let's have here next deduction of Euler's theorem. Now this is of second order, right? Now same procedure we have to use here that we used for u when it is homogeneous of xy of degree n. Okay, so see here, first of all, as I told you, always write down a given part. Okay, so what is given here? Yes, z is homogeneous function of x and y of degree n. I hope you all understood the first three proofs that I have taken here. Okay. Now see, z is given to us homogeneous of xy of degree n. So by Euler's theorem, let me write Euler's theorem. What I can write? X into, see z is homogeneous, so I have to write here z. X into dou z by, yes, dou z by dou u plus y into dou z by dou y, dou z by dou x plus y into dou z by dou y is equal to nz. Also, we have already proved. What we have proved? Yes. It is x into dou u by dou x plus y into dou u by dou y is equal to n into f of u upon f dash of u. Okay. See the difference between two. I have written here dou z by dou x, right? And here dou u by dou x. Functions are changed. When you are going to write z, it will be nz because z is homogeneous. But when you are going to write u, since z is homogeneous, we have to write instead of z f of u upon f dash of u. Okay. So this you have to remember. Okay. Now I have to consider here let n into f of u upon f dash of u is equals to g of u. Let's consider this value. So here equation then becomes x into dou u by dou x plus y into dou u by dou y is equal to n into g of u. Okay. So I hope you all understand. Now see. I'm going to differentiate this, say this is our equation 1. This equation with respect to x again, because what I want here double derivative, right? So differentiate equation, let's say this is an equation 1, right? So equation 1 with respect to x, keeping y constant. Okay. So here we have to keep y constant and we have to differentiate with respect to x. So these also depends on x and this function also depends on x. So we have to use here product rule. So if suppose x is constant and I take a derivative of dou u by dou x, so that will give me double derivative of u with respect to x. Plus, now suppose I keep this dou u by dou x constant. Okay, see here you can see I have to use your product rule. So if I suppose keep this dou u by dou x constant and derivative of x, what is it? 1. Okay. Plus, now derivative of this term with respect to x. Now y is constant, so I have to just differentiate this one. But already this is a derivative with respect to y. So when I differentiate with respect to x, I will get here double derivative, that is a mixed derivative of u with respect to x and y. So I can write here y dou to u upon dou x dou y, that is equal to, see, n into g of u, right? This g of u is depending on x, so I have to take a derivative. So I can write here n into g dash of u, and derivative of u is dou u by dou x with respect to x. Okay. But you can see here this double derivative is multiplied by x square, and here our double derivative is multiplied by x only. Yes, definitely we have to multiply here this equation by x. So multiply by x. What it will give us? X square dou to u upon dou x square plus x dou u by dou x plus xy dou to u upon dou x dou y is equal to n into g dash of u into x dou u by dou x multiplied by x here. Okay. Now say this is our equation A. Now to find double derivative with respect to y. So here I have to differentiate equation 1. Yes, with respect to y, keeping x constant, right? So here when I differentiate equation 1 with respect to y, see your first term, only this single term is depending on y. So I have to take a derivative of this term only. So this time x is constant and this will give me the mixed double derivative dou to u upon dou x dou y plus. Here I have to use product rule because y and dou u by dou y both are depending on y. So by using a product rule I can write, suppose y is constant, dou to u upon dou y square plus, now dou u by dou y is constant and derivative of y is 1. That is equal to n into g of u. It is again g dash of u. But this time the derivative is with respect to y. Right? But if you see here in our proof, this double derivative of u with respect to y, it is multiplied by y square. And here it is multiplied by only y. So we have to multiply here equation by y. So multiply by y. Okay. So what it gives us? So here when I multiply the equation by y, it will give me, multiply this equation by y. So xy dou to u upon is a mixed double derivative. So I can write here dou x dou y plus, now multiply by y. So that will give me y square dou to u upon dou y square plus, and this one will give me dou u by dou y into y, means that will be y into dou u by dou y. Okay, and on right hand side, yes, it is n into g dash of u y into dou u by dou y, right? Okay, now here say this is our equation B. So adding these equations together, so equation A plus equation B, if we do on left hand side, if we do the addition, what I get, see here, now you all understood when I do the addition what should be the right hand side, this derivative and this derivative, that will be 2xy dou to u upon dou x to y. So I am directly going to write here addition, just cross check after when you solve the example. That will be, see, addition x square dou to u upon dou x square plus 2xy dou to u upon dou x dou y plus y square dou to u upon dou y square plus x into dou u by dou x plus y into dou u by dou y is equal to n into g dash of u is common, and what is remaining, x into dou u by dou x plus y into dou u by dou y. But we all know what is the value for this x into dou u by dou x plus y into dou u by dou y. See here, you can check, x into dou u by dou x plus y into dou u by dou y is equal to n into f of u upon f dash of u. But for this we have taken an substitution g of u. So according to this, I can write for this x dou u by dou x plus y dou u by dou y is equal to g of u, right? So using this value here, what I get, x square dou to u upon dou x square plus 2xy dou to u upon dou x dou y plus y square dou to u upon dou y square plus, yes, it will be it will be only g of u, right? That will be equal to, just a minute, I think something is missing. Yes, we have to just simply write g of u only. Okay, little correction is here. Actually, we have taken here n into f of u upon f dash of u is equal to g of u. So, this complete term will be replaced by g of u. This n should not be there. So, I have to just not to write here n. Then here also there will not be n. Okay, we have to remove this n from here. Okay, here also there will not come any n. Okay, only just g of u we have to use, and then this will be g dash of u, and this is again I can use the substitution g of u, right? And on next, what I can write, x square dou to u upon dou x square plus 2xy dou to u upon dou x dou y plus y square dou to u upon dou y square is equal to, transfer this g of u on right hand side. So what I will get here, g dash of u into g of u minus g of u, And when I find here g of u common, what is remaining? Yes, it is g dash of u minus 1. Where? Definitely, what is the value for g of u? It is n into what? Yes, f of u upon f dash of u. This is a value for g of u. So I hope you all understood all these 4 statements and proof. Okay, these all proofs are important. Any of the proof can be asked in your examination. Okay, so thank you all for watching this video.